Hello everyone, welcome back to Diksha Karnataka YouTube channel and welcome to Decode NCERT series where I am trying to help you with all the chapters from your NCERT one by one. Today is the time for alternating current. So alternating current is one of the major important chapter in terms of concepts, also in terms of the weightage of your PU board exam. You can expect one numerical questions coming from this chapter. Also a lot of question comes for KCET exam as well, JEE exam as well. So this is a very important chapter. So without any delay, without much introduction, let's start with this chapter because this chapter does not need much introduction. We have an introduction given for this chapter. So let's look into that introduction given in your book. Okay, so what is that? So you can remember this part. Okay, other than that nothing much is there. Let me zoom so that you can see it clearly. Also I request you, if you don't have the book with you yet, open your NCERT book and mark these lines. These are very important lines. Some are for just to gather knowledge, some is to clear any doubts, any misinformation that you might have. So everything is important here. Let's see. So here the electric mains supply in our homes and offices is a voltage that varies like a sine function. So what is a sine function? If you remember, or if you have seen that a sine function basically is something like this, right? You remember that this is something like a sine function. So the supply, even the cosine function is also a type of sine function. Okay, any function or any combination of different sine functions can be considered as sine function. Sine function means it's a tangent trigonometric function basically. Okay, not directly a tan function. Tan is, we know that tan goes to infinity at some angle, so that's why we ignore that tan. But sine, cos, or addition of sine a sine x plus b sine y, they are all considered to be sine function. Right now, the electric mains supply in our homes and offices are voltage that varies like a sine function with time. Such voltage is called alternating voltage or AC voltage. Okay, and the current driven by this circuit is called alternating current or AC current. Now this is interesting. There is a asterisk given over here. Okay, you can see the asterisk given here. Why it is given? Because we say that alternating current. So in short form it should be only AC, right? But we often say, it is very common and we actually accept that it is not incorrect, that we say that AC current. Okay, what is the meaning of AC current? AC itself means alternating current. So AC current means alternating current. So here we are saying current twice, which is interesting, right? But it is widely accepted because there is another version of current, direct current, so which is we often call direct DC current. Okay, and DC voltage. So DC voltage is nothing, there is a direct voltage, but instead of saying dV we say DC voltage. Okay, we liked this term and this is how it was used for long, and it is not you are not the first, not me. Okay, some time back they started using this term AC current, DC current, and since then it is continuously going on, even though it's a redundant. Redundant means using more than once, right? So if I say my name is my name, so how does it sound? Does not sound good, right? So that's why it is like a redundant use. More than once it is being used, and but we accept that. So this is one case, even though it is not grammatically or English wise correct, but still we accept it because it is used by people for long time, and now it is accepted worldwide. Not only in India, not only in our country, it is accepted worldwide. Now this is just a side story. The main reason for preferring use of AC voltage over DC voltage is that AC voltages can easily be efficiently be converted from one voltage to the other by means of transformers. Further, electrical energy can also be transmitted economically over the long distances. So that is the main reason that AC voltages are used. We will see that in a while. So basically, what is the meaning of that? Applying Ohm's law, we can convert voltage and current in terms of power consumed, right? P is equal to V into I, or P is equal to V square divided by R, right? Now, if we can keep the voltage low, so if we can keep the voltage low, basically keeping if we can somehow increase the instead of increasing the current, if we keep the voltage high, then instead of square, the power consumed in the circuit will be less. Okay, so there is a proof of that if you keep the current high, there will be loss, there will be higher loss compared to if you keep the voltage high. Okay, because in terms of current it is I square into R. Now R you cannot decrease by beyond certain level, right? So you have, even if you use platinum wires, even if you use silver wires, okay, you cannot decrease the resistance beyond certain limit. Okay, everything has a resistivity, we have already learned that. But if we can change the formula to V square by R, and if we can increase the R instead of decreasing it and keep the voltage higher, then the power consumed in the circuit will be much less. Okay, so that is how we keep the current low and voltage high to reduce the power loss in the supplying wires through which the current reaches your house to minimum. Okay, that is the main reason, and this is possible for AC. Okay, maybe it sounds little confusing, we will see that in a while completing the chapter, but this is easily possible for AC rather than DC. DC cannot be easily converted from higher voltage to lower voltage or lower voltage to higher voltage. Okay, you have to do a lot of work to do that, but for AC it is easily possible. So we save a lot of money while transporting the current from the source to your house. Okay, that is the main reason. Okay, there is no other reason, and based on that, because AC is commonly used, all the designs, all the machines that functions today are based on this AC current. Okay, maybe in future when we fully switch to solar power, okay, maybe DC will make a comeback, maybe we will use DC more than AC, but that is for a different discussion, different time, not in this class. Okay, now AC voltage is an applied resistor. Now voltage, AC voltage generally represented by V is equal to Vm sin omega t. What is this? If you remember in your SHM chapter, that whenever we are representing an SHM, we used to represent is using the similar term, right? So Y is equal to A sin omega t. Here omega is the angular frequency or sometimes angular velocity of the input voltage. Okay, Vm is the maximum value of the voltage, that is the peak voltage, we call it peak voltage, the maximum value, okay, or amplitude of the voltage, and omega is the angular frequency. This is the form that we use to solve problems, solve numericals in our AC. Right, now when we are trying to find the current in the circuit, when we are trying to find the current in the circuit, the maximum current, okay, the amplitude of current or peak current is given by peak of the voltage divided by resistor. Now here what we are doing, we are only applying AC source. This is the symbol for AC source. AC source is applied to a resistor alone. Okay, we know that what is the symbol for DC source, right? Here we are, DC source is represented like this, right? This is a DC source, but DC source supply voltage steadily. It does not represent the variation of voltage, so that's why AC sources are represented like this. Okay, should remember that. Now clearly the voltage and current are in phase with the one with the other. Why in phase? If you see, the expression for current is given by I is equal to Im sin omega t. What was the voltage? Voltage was V was equals to Vm sin omega t. Right, now if you see that here also sin omega t, here also sin omega t, so both of them have same sin omega t, nothing is plus or nothing is minus, that means they are called in phase. If you find two functions which have same trigonometric relation, then we say they are in phase. Okay, so this is one important thing, that in case of only resistor applied, AC applied to an only resistor, the current and voltage will always be in phase. Okay, one more important thing is here is this diagram. Okay, so if you see that when the current is maximum, voltage is also maximum. When the current is 0, voltage is 0. So both of them are starting from 0, going to maximum together, coming back to 0, again going to minimum together, and then going to maximum, going to 0 again together. So they are like perfect friend. So that's why they are always walking together. So one is doing engineering, another one is studying doctor, but both of them started from the same line. They are completing their courses equally without any fail. So for example, when you move on to the future life, you might connect it in future, right? Now let's move on. So now we know that power in DC was given by I square R. Right, now in case of AC, I square R does not have much sense because there is a sine square term involved with the current, right? So what we have to do, we have to take the average of this sine square omega t. Now sine square omega t's average turns out to be half. Okay, average of sine is 0, average of cos is 0, average of sine square is half, average of cos square is half. There is a small derivation given in the footnote, you can check that out how it is like that. And the average power in AC circuit comes out to be half I square Im square R. So Im is the maximum power, maximum current, and R is the resistance. So this is the power absorbed by an AC circuit. So in AC circuit, if you are giving a DC current of Im and resistance R, the power absorbed is I square M. Right, but in AC circuit it is already half. At the beginning of this is already half of that value, right? So that's why AC is common. Okay, now to express the power in the same form as DC power. So in the DC power, our formula was I square R. If you remember, a special value of current is defined and used. It is called root mean square RMS, or effective current, and it is denoted by IRMS or capital I. So capital I generally, remember that capital I is generally used for DC purposes. Okay, DC current, DC sources. Whenever we are talking about DC, we say capital I. But in case of AC, if you know this is AC and the capital I is there, that means this represents RMS current. Okay, it is sometimes written as IRMS. Some people like to write it I capital IRMS. Both are okay. Some people like to write only capital I. Everything is okay, but you have to remember that everything is equal to maximum value of current divided by root 2. Now why it is important? Because as we know that current in case of AC circuit is not constant. Unlike in DC the current was constant, right? But in AC it varies like a wave. So what is the effect of effective current? What is the actual current that we are receiving? It is varying from 0 to maximum, then maximum to 0. Right, so IRMS gives you a value which is actually effective current, which is the IRMS is slightly less than that of the maximum value. So because why, you can see that it is basically 70% of the maximum current. Okay, so IRMS is basically 70% of the maximum current. 70.7, but approximately 70%, right? So whenever we say IRMS, suppose for example we say 220 volt supply. 220 volt supply is the RMS voltage. Okay, if I say the circuit, the bulb can withstand say 2 ampere current, that 2 ampere current is an RMS current. Okay, these are very, very important. So for our day-to-day life, wherever you see 220 volt, 440 volts, they are all actually represents RMS value. Actual maximum value is higher than that 220 volts. Okay. The average part I said that is proved here. You can check this out, how to calculate the average. I am not going to do that. That is a mathematical part. Anyway, now the RMS current is defined by Im by root 2, that is 0.7 Im. So now the power in the circuit is given by I square R, that is now similar to that of our expression we used in DC. Similarly, voltage also is defined by Vm by root 2, that is 70% of the maximum voltage, right? Now from there we can write the Ohm's law. Now Ohm's law, again it is valid for AC circuit as well. V is equal to IR, right? So Ohm's law is again applicable for RMS when you are using maximum voltage, maximum current, or you are using RMS voltage, RMS current, right? So this is valid. So the example I was talking about, they have also given. For example, the household line voltage of 220 volt is an RMS value with the peak value voltage of 311 volt. Okay, so the peak value of the voltage is 311, which is quite higher than 220 volt. So sometimes there was a question when I was a student that why AC is more dangerous than DC. Okay, because if DC says 220 volt, that means the maximum value is 220 volt, the minimum value is 220 volt. There is no difference between that. But in case of AC, if it is says 220 volt, actually it means that the maximum value can go up to 311 volt, which is dangerous, which is much more. The maximum value of the voltage can cause higher damage to you than a DC voltage. So a DC 220 volt can damage up to 220 volt only for your body, but at 220 volt AC can damage your body up to 311 volt, which is very fatal, which might burn your body and you might die. So do not touch any AC wire without expert assistant. Okay, this is very, very dangerous. Current is not something that to play with, right? Now power is equal to V square by R, and you can calculate that. Again it is VI, Vodafone Idea. I asked you to remember like that, but they written it like IV, that is 4. That is also whatever you are comfortable with, you can remember like that. But anyway, this formula I was talking about, power can be represented by V square by R. So using this formula, if you can somehow increase the R, even if the V is high, you can actually reduce the power. In case of current, if the current is high, then it will multiply with the value of the current. Okay, now let's move on. Now representation of AC current and voltage by rotating vectors are called phasors. Phasors are very important concept. Okay, in higher physics, if you study physics in higher class, definitely you will learn a lot about phasors. Phasors diagram will be there in sound as well. But in this chapter, what you have to remember is that phasor is basically a way to represent something which is changing, right, with time. The analysis of an AC circuit is facilitated by use of phasor diagram. A phasor is a vector which rotates about the origin with angular speed omega. Okay, so angular speed omega is with which a vector is rotating. So basically we have learned in our simple harmonic motion that a simple harmonic motion can be represented by a circle. So this is kind of that circle only. Okay, but we do not draw the circle completely. What we draw is the only thing we interested is the relative phase. So these two phase arrows are important, right? So what we do is that we draw these arrows to represent different quantities. For example, here the blue arrow, if you see clearly, represents the voltage, and this dark gray arrow represents the current, right? And both of them are at same phase, that's why they are one over another. Okay, so this is a representation of AC current and AC voltage, which is used to represent. It is not a real vector. Okay, you have to remember that this is not a real vector. This is only used to represent, right? Now let's move on. AC voltage applied to an inductor. This is a expression, this is a formula. Even though the derivation and explanation is not super here, you just need to put the value. Super difficult here. What you have to do, you have to just put the value and calculate what is the current here, and once you find the current you will get is minus Vm by omega L cos omega t plus constant. Okay, now you can put the constant to be 0. Okay, if you take the initial value to be 0, starting from 0, it is reaching some value I, then you can make this constant to be 0. But what about this minus cos omega t? Okay, minus cos omega t can be written as sin omega t minus pi by 2. Okay, you can check that out. Complementary angle formula, a simple mathematical complementary angle formula. If you apply that, you will get that minus cos omega t is equal to sin omega t minus pi by 2. So you can write current I in terms of sine. Now if you see the voltage, when we started, our voltage was, what was our voltage? Voltage was V equals to Vm sin omega t. Now after finding the current, we see that voltage was sin omega t, current is some value Im multiplied by sin omega t minus pi by 2. So both of them do not have the same phase, that much is clear, right? Also here that value Im is turning out to be Vm by omega L. If you remember, in our resistance Im was Vm by R, right? Now here instead of R, this quantity omega L actually behaving as R, right? So only when an inductor is connected with an AC circuit, okay, so this omega L is behaving like resistance. That's why it is called inductive reactance. Inductive reactance is kind of resistance, but it is only active in AC circuit, and it is being applied by an inductor. Okay, that's why it is called inductive reactance. Okay, and its unit is obviously ohm. It's very, very important. Sometimes they might ask you an objective question, what is the unit of inductive reactance? Inductive reactance is nothing but a type of resistance, so its unit is ohm. Okay, and this value inductive reactance, in short we write it with XL. XL is the value, and the XL is the representation, and omega L is the value. And now we can write Im is equal to Vm by XL. Now what is the phase difference here? As you can see, voltage and current is lagging. Current is lagging by a phase of minus pi by 2. Okay, so current phasor I is pi by 2 behind the phase, behind the voltage phasor of V. So in case of only inductor in a circuit, current is lagging in phase. We say current is lagging. Lagging means behind. Okay, lagging behind or only lagging, both are okay. So what is the meaning of that? If you draw the phasor diagram, as you see, voltage is ahead and current is behind. So your exam dates are coming, but your study is falling behind. So you are falling behind in your study, but your exam dates are coming faster. So that is why it is called lagging in phase. But if you have already completed your syllabus and your exam dates are coming, that means you have already ahead, your syllabus is completed and you are leading. We will see that in the next part, which is leading, which is lagging. So basically, when the voltage was 0, current was in negative. Now when the voltage is maximum, current is in 0. When the voltage is again in 0, current is maximum. So after your exam is over, you have completed your study, which is not helpful, right? So that's why I say continue your study, don't waste your time. Now let's start, let's continue. with the AC voltage applied to a capacitor. Rest of the parts you can read it once, okay, not super important. Okay, now again similar to that of inductor, we can again find the relationship. Mathematical proof derivation is there. Mathematical derivation is not important for your board nor for your any competitive exam. Definitely you should just have a look into it in case if you are preparing for JEE mains exam. Sometimes they might give you a function and they might ask you to find the current. So in that case you have to do the differentiation, that's it. So differentiation, you just check it once. Now in this case, as you can see, the formula was only cos omega t. So cos omega t can be written by sin omega t plus pi by 2, and after doing everything we have found one more quantity xc. Okay, xc is given by 1 by omega c, that is called capacitive reactance. Okay, this is another important term, capacitive reactance. Okay, so and capacitive reactance is represented by 1 by omega c, and again 1 by omega c has the same unit as omega L as R. So 1 by omega c's unit is again ohm. So what is the unit of capacitive reactance? Ohm. Okay, and symbol is obviously that omega. So that amplitude of the current is again given by Im is equal to Vm by Xc, and it is leading in by phase. Okay, so leading by pi by 2 phase. Okay, phasor diagram instant. Here the current phasor I is pi by 2 ahead of the voltage phasor V. Okay, so as you can see in this case, the diagram, if you see clearly that voltage is now behind, current is ahead. So when the voltage is 0, current is maximum. When voltage is maximum, current is 0. Again, when the current voltage is 0, current is negative. So basically what is happening, before your exam comes, you have completed the syllabus. So this is how looks like. So decide yourself what you will like to be, a capacitor or be an inductor. Okay, inductor means who opposes everything, capacitor means who accepts everything. That is the difference, right? Now in case of inductor and capacitor, okay, as in the case of inductor, the average power is 0. So thus we see that the case of an inductor, this is the summary of everything which is important. In case of inductor, the current lags the voltage by pi by 2, and in case of capacitor, the current leads the voltage by pi by 2, and power consumed in both the circuits are 0. So power consumed, average power consumed in an pure inductor is 0, average power consumed in an pure capacitor is 0. This is a very important line for your MCQ questions, right? Now AC voltage applied to an LCR circuit, this is a complicated equation. Obviously you don't need to solve it, okay, before you move into the graduation. If you study, I think in physics we have solved, I am not sure in electronics if you have to solve it or not. This is called series LCR circuit. Okay, series LCR circuit means series resistance. You have learned about series resistance. So one is connected after another. So series LCR is basically when an L and C and R are connected in series. There is a combination which is called parallel LCR, that is not part of your syllabus. Again, that is a little complicated than this. Okay, and after solving this, you can get that current is equals to Im sin omega t plus phi. There is a derivation, the geometric derivation given for this part, but that is not required. Okay, eventually you will get that Vm square, okay, is equal to Vm square is the input voltage, maximum of the input voltage. Vrm square is the voltage across the resistor. Vcm is the voltage across the capacitor, and Vlm is the voltage across the inductor. So this is the common formula, and if you want to find Vm, then it will be square root of this thing. Okay, so this formula is very, very important. And again, the current formula is very, very important. Vm by this value. What is this? This is called impedance. This is called the impedance of an RLC circuit. This formula is very, very important. All these formulas are super important. Okay, based on this, any moment any numerical can come. Okay, so these are the formulas from which questions will come. Okay, and this is the phase difference. Phase difference means the angle. In case of pure capacitor, it was leading by pi by 2. In case of pure inductor, it was lagging by pi by 2. Now when you, and in case of resistor, it was 0. Now when you mix all three of them, you cannot expect a fixed value. Definitely based on what is the value of XC, what is the value of XL, you will get a phase difference, and phase difference can be calculated using this formula: tan phi equals to XC minus XL divided by R. Okay, now if XC is more than XL, then the circuit is said to be capacitive. Okay, and current will lag behind like a mistake. If XC is greater than XL, then we say this is capacitive and current will lead. Okay, like in a capacitor. But if XC is less than that of XL, okay, then the circuit is inductive, and we say that current is lagging behind. So like in a pure inductor. Okay, whatever the circuit is, that depends on that. We can say it is capacitive or inductive, and if it is inductive, it will take the characteristics of an inductor. If it is a capacitive, it will take the characteristics of a capacitor, right? So phasor diagram, everything is there. This is the phase difference. Okay, general phase difference, not super important, but I just thought, okay, now we have seen two cases where XL is greater than XC or XC is greater than XL. Both cases we have seen. Now what will happen if both of them are equal? That case is called a resonance condition. Okay, resonance. So at resonance, if XL equals to XC, then so with XC equals to 1 by omega C and XL equals to omega L, so if omega is varied, then at a particular frequency XC equals to XL, and the impedance is minimum, that is XL minus XC whole square, that becomes 0. So Z equals to R. This frequency is called resonant frequency. So at a certain frequency, when XL is equals to XC, the both values matches, that point the circuit is only a resistive circuit. There is no capacitor or inductor. That is called a resonance frequency, and the frequency is given by, the angular frequency is given by 1 by square root of LC. In exam, you will be asked to find the actual frequency, which is 1 by 2 pi square root of LC. You need to remember that omega is equal to 2 pi f. This is the relationship between angular frequency and actual frequency. Okay, angular velocity, basically angular frequency we say, but this is actually angular velocity. Okay, they have given some example, and at resonance what happens, you have to see that normally the current is varying like this, but at resonance the current becomes maximum. Okay, at resonance the circuit becomes maximum because there is no effect of inductor or capacitor to the current. So current is only controlled by the resistor, so the circuit becomes resistive. So this is also an objective question, that at resonance the circuit is capacitive, inductive, resistive, none of the above. So you have to choose, it becomes resistive, right? Now it is important to note that the resonance phenomenon is exhibited by a circuit only if both L and C are present in the circuit. Now R is not mandatory, but L and C both has to be there. It is not possible if you connect only R and L or R and C. Okay, there was two circuits in the past, that is not no longer part of the syllabus, but still question might come from RC and RL circuit, because if they ask you, there is an important thing, that if they ask you what will be the impedance in case of RL circuit, only R and L is connected. So in that case, what you have to do, we have to put XC equals to 0. If they give you only RC circuit, then what you have to do, you have to put XL equals to 0. Okay, and if they give you LC circuit, then you have to put R equals to 0. LC oscillation was part of the syllabus, but LC oscillation is also no longer part of the syllabus, which was really complicated at that point of time. Since pandemic, that is difficult part is now removed. Okay, now also there are some bandwidth from formulas etc. that was there, but that is no longer part of the syllabus, so I am not going to discuss that. Only then do voltages across L and C cancel each other if both being out of phase and the current amplitude is V by R. The total source voltage appearing across R, this means that the we cannot have resonance in an RL on an RC circuit. Okay, so RL and RC circuit cannot have resonance, it is only possible in RL circuit. So if they ask you which of the following circuit resonance is possible, RLC series, okay, RL circuit, RC circuit, or maybe they will ask none of the above or all of the above, then you have to mention only RLC circuit or LRC circuit, LCR circuit, whatever formula, whatever name you use. So LCR, RLC, they are same, okay, or LRC. We generally do not start with C. I do not know, we do not have any name with C starting with CLR or CRL, but LCR, LRC or RLC, the three are acceptable names. Okay, the power factor, this is a very important term. So power factor is determined by the phase. Okay, if the phase is phi, then the power factor is basically nothing but cos phi. Okay, so if the phase in a series LCR circuit is phi, then the power factor is cos phi. Okay, here this cos phi is called power factor. Let us discuss the following cases. Resistive circuit, if the circuit contains only pure R, it is called a resistive circuit. In that case, power factor is in this case phi is equal to 0, cos phi is equal to 1. The maximum power is dissipated. Okay, now there are few cases also given. In case of purely capacitive circuit, the circuit contains only an inductor and capacitor. We know that the phase difference between voltage and current is pi by 2. That means cos phi becomes 0, so no power dissipated. Similarly, in case of LCR circuit, in an LCR series circuit, power dissipated is given by cos phi is equal to exactly whatever the phase difference is given. So they might ask you what is the power factor of the circuit. So if they ask you what is the power factor of the circuit, first of all you have to calculate XL, then XC, then tan phi, then tan inverse phi, and then whatever the phi gives you, cos phi will be the expected value of the power factor, right? Power dissipated at resonance in an LR circuit, again power when we are talking about resonance, at resonance phi becomes 0 again, cos phi becomes 1 again. That means power dissipated is again maximum. So power dissipated in a circuit is maximum when circuit is in resonance condition. So these are the important thing to know from this chapter, and I think we have completed this chapter. One more thing, another important concept is there, transformers. Even though transformer is actually related to electromagnetic induction, but because it is application of AC current, that's why it is given in this chapter. So we said that we can change the voltage of a AC source quite easily. How to do that? Power supply of AC source can be increased or decreased by a device called a transformer. Transformer is a very common device. You may have seen it in outside your home or outside your society. It's like a post, okay, with a big box kind of structure is there. Okay, old generation television, if you have seen behind backside of an old generation television, it's covered in a box. So that is called a transformer. Sometimes we say the transformer is blown out. Okay, transformer is burnt, so transformer needs replacement or something like that. So that is a very common scenario across India, even if we are a lot of developed than past. Okay, in past when I was child, maybe it was happening once in a year. Maybe right now it's happening once in 2 years or 3 years. The frequency has decreased, but still this is happening in many places, right? Now what is the transformer? One of the coil is called primary coil NP. So there are two coils in a transformer. One coil is called primary, the other coil is called secondary. Okay, primary coil has NP number of turns, secondary coil has NS number of turns. Okay, the primary coil is the input coil. Input coil means whatever power you are applying, that power should be supplied to the primary, and from here we will collect the power. Okay, this is our point of collection. Okay, so this is from power coming from the power station goes into the primary, and from there it is converted into secondary, and secondary send this to our home. Okay, basically most of the transformer that we use in our locality are step down transformer. Step up transformer is used in the source power station, okay, where the power is generated. Now there are some relationship you have to remember that first of all, first relationship is Vs by Vp is equal to Ns by Np. Okay, direct relation. So power consumed in a secondary of coil is equals to secondary number of turns in secondary divided by primary of voltage equals to number of turns in primary. So easy to remember. Also in case of ideal transformer, it is important to know that the power input is equals to power output, and since P is equal to Vi, we can write Ip into Vp is equal to Is into Vs. So total power is in primary, this is the power in primary, this is the power in secondary, they has to be equal in an ideal transformer. Okay, but you do not need to remember all these formulas. Okay, two formulas are sufficient to solve all type of problems. First of all this formula, secondly this formula. Okay, and if you are you have a super good memory, you can remember these formulas, individual formulas as well, but based on the problems you have to modify it anyway. So that's why I request remember the two good formulas, mother formulas. From there you can solve all the problems. Okay, that is, if the secondary coil has a greater number of turns than the primary, the voltage is stepped up. So if the number of turns in secondary is more, so for example I have designed a transformer such that in primary I have 10 turns. Okay, in secondary I have 100 turns. So what is happening here is that in this case the input voltage, whatever input voltage I am applying and whatever output voltage I am getting, output voltage is more than that of input voltage, and this is called a step up transformer. So not step up dance movie, step up transformer. Okay, and in if it is opposite to that that is the number of turns in the primary is more, number of turns in secondary is less, then this is called a step down transformer. Okay, step down transformer. In electronics, if you study electronics engineering, okay, so if the number of turns in the secondary is less compared to the primary, we call it step down transformer, which is used in our household. Most of the common transformer that we see in our society are actually a step down transformer. Okay, but in actual transformer, small energy losses. So ideal transformer, we said that there are no energy loss, right? All the power input is equals to power output, but in actual transformer there are different types of losses, and we cannot stop it. First of all, flux leakage. What is the flux leakage? Flux leakage means the field lines exiting from this coil. Okay, there are all possible field lines, but only few of the field lines is actually cutting this coil. So basically this transformer works under the principle of mutual inductance, right? So whenever current varies in this coil, the same magnetic field linked with the secondary also changes, and there is a induced current in the secondary. That's how the transformer works, right? So this is the basic working principle of a transformer. You can read that working principle of a transformer. Sometimes it might come as a 2 to 3 marks question, but according to the current all three blueprints, there was no 2 marks or 3 marks question from this chapter, so that's why I chose to exit it. But in case if you have any doubt, you can study that part as well. Now the flux line, the field line that is exiting from the primary, does not necessarily all of them will connect the secondary, because it's a finite size, and we know that magnetic field lines have infinite direction. Some of them might come in this direction also, right? So this 50% of the energy is already lost. So to decrease that, there is another way. They have shown you one more connection here, is this kind of connection, right? So this is called same coaxial coils. If you connect them like this, okay, there is a chance that the flux leakage is less. And modern transformer use different types of phase transformer as well. If you study electronics, electrical engineering, you will study them in detail. okay, different phase 1, phase 2 transformer, okay, but that is one of the way to decrease the flux leakage. These are important points. Based on that, objective questions might come. That's why these are included. Again, it can be reduced the windings of the primary, okay, coils come over the other. So basically the way I said, coaxial, if you make them coaxial, you can reduce the flux leakage. Resistivity of the windings, okay, resistance of the windings that you are using are not ideal conductor. They have some resistance, so some heat will be generated within the conductor itself, so there will be some loss. Already some loss will happen, okay. It will happen in primary as well as secondary. Both cases, whenever there is a current developed according to Ohm's law, some current will be, some resistance will provide, some resistance will try to stop the current flow in it, and based on that, Joule's law of heating, some heat will be definitely generated, and that heat loss will be definitely there, okay. That heat loss can be reduced by making the wires thicker, okay. If you make the wires thicker, resistance will decrease, and based on that, you can somewhat reduce the heat developed, but you cannot completely reduce it. Now eddy current is some interesting concept, okay. I cannot explain the basic thing about eddy current, but if you have seen some experiment, there is a copper tube. Through that copper tube, a magnet is dropped. The magnet falls very slowly, okay. In comparison, if you drop any non-metallic substance, any non-magnetic substance, it falls very quickly, but in case of a magnetic substance, it falls very slowly. Why is that? Because there is something called eddy current. Eddy current is something when a current changes, okay, we use a core, right? The structure that we have seen, this structure, this is called the core of a transformer, okay. This helps to link the flux. So this helps, whatever flux is not directly getting connected, this core actually helps to link the flux with the secondary. Right now, the core itself is metallic. So what is happening here is there is a flux changes in this primary. This flux change is also affecting this core. Okay, so due to that, the core itself starts getting some current, okay, some current flowing in this core, and that core that can lead a heating up of the core. Also, the energy supplied by primary is getting wasted by this current developed in the core. Okay, so that is called eddy current. This current which is developed in this circuit are called eddy current, and one of the uses of eddy current is that the metal detectors that you have seen in airports or in shopping malls or in anywhere, you have seen that they are checking your body. That is a use of eddy current. Okay, so eddy current can help to determine whether you have some metallic objects in your body or not. Okay, so that is the function. Okay, this effect can be reduced by using a laminated core. Laminated core means what they do, if you have seen old generation TVs, they used to have a transformer, okay, because they require a different voltage than the supplied voltage. That's why they used to have a transformer. So in that, instead of using a single piece of metal like this, what they do, they cut this piece into small plates. Okay, now all the small plates are stacked together, and then they are bind together using wires. Okay, so this is called laminated cores. Basically what they do, they add insulating materials, okay, like wax or some gum, okay, so that the metal it is not a continuous metal block. Okay, it is a stackable individual layer of very thin layer of conductor. That way you can reduce the eddy current developed in the circuit, and you can reduce the heat generated. But still it is still there. Obviously you cannot fully eliminate it, but you can reduce it significantly. Another is hysteresis. About hysteresis, again the hysteresis part is completely deleted from your syllabus. What is hysteresis? I can say that hysteresis basically when the current is going maximum, then 0, then minimum, again 0, then again maximum. So current voltage is changing the direction. Similarly, the current is also changing the direction. Now due to this changing direction of current, the magnetization of the material of the core also changes every second. Okay, 50 times. So 50 Hz means the current changes direction 50 times every second. Similarly, the magnetic field also changes its direction 50 times in every second, right? So that's why because of the changing of the magnetic poles, okay, there is a electromagnet. Basically it's like a electromagnet, right? So electromagnetic pole changes happens very quickly. So that's why the magnetic material used in the core of the transformer gets heated up very quickly. Okay, so that can be reduced by using a material which has a very low hysteresis loss. For example, iron. Okay, iron has a core which can use to reduce the hysteresis loss. Now they have given you some example how can you cut down the losses, etc. Okay, you can read this paragraph. This is for a practical usage rather than exam usage. Okay, I hope you enjoyed this session. This session is slightly longer than average because this is a application oriented chapter. You can check the dimension table given in this part. So as I said, inductive, capacitive, impedance, all of them have the same dimension, and basically they are all nothing but resistance. Okay, I hope you enjoyed our session. I'll be back with a new chapter next week. Till then, bye.